y'all. You ain't making me sick. People have known for a long time that different elements give off different colors when they're exposed to a heat source, like a flame or an electric current. I mean, that's how fireworks work, and we've known about those for a long, long time. And around the 1800s, people learned if you take that light and you pass it through a prism, it'll take that color and split it up into all the individual colors that make up that light. And this is what we call an emission spectrum. And it's basically the same idea as when you take white light and shine it through a prism, but instead of getting the whole rainbow, you only get the colors that make up the color that you're seeing. And as people continued to study emission spectra, they realized that every element had its own unique one, which pretty much gave it its own fingerprint. And as people tried to figure out what was going on here, a lot of people focused on hydrogen because it had the simplest emission spectrum. And if you're going to start studying something for the first time, it kind of makes sense to go simple. And around the late 1800s, a guy named Rydberg looked at the emission spectrum for hydrogen, and he came up with this equation called the Rydberg equation. Yeah, we're good about naming stuff after ourselves. Scientists are egotistical that way. That related the wavelengths for each line in the emission spectrum with these numbers that he just called N. So this is a common way to show the Rydberg equation. In his equation, again, lambda is the wavelength, like you've seen in other places probably. The N's are just any positive whole numbers, 1, 2, 3, 4, etc. And the reason I like to show it this way is that it's easy to remember which N goes in which place, because the NB is the bigger of the two numbers, which that's convenient. So for example, in the visible part of hydrogen's emission spectrum, Na is 2, and again, NB is just any bigger number. So when NB equals 5, if you plug 2 and 5 into the Rydberg equation, along with the Rydberg constant, that gives you 4.34 times 10 to the negative 7 for the wavelength. That's in meters. If you convert that to nanometers, you get 434 nanometers, which is this line in the emission spectrum. One thing to remember about Rydberg's equation is that it's solely based on data. He just looked at all the little lines in the emission spectrum and he come up with an equation that matched the lines to these magic number N's. What those N's were, nobody knew. But as people started to study the atom more and more and realize that you had protons and neutrons in the middle in this nucleus and you had the electrons around it, people started to develop an idea of how those N's related to an atom, specifically the arrangement of electrons around that atom. So in the early 20th century, a guy named Niels Bohr tried to explain those magic N's in Rydberg's equation by saying that they were the equivalent of the different energy states that an electron could be at as it orbits the nucleus. Well, orbits the nucleus. Later on we'll see it technically doesn't. But at this point, if you want to think of it as orbiting a nucleus just like planets orbit the sun, that's fine. And if you want to think about these N's as distances from the nucleus instead of energy states, that's perfectly fine, especially in a first-year gen course. This is general. Let's keep things general. So Bohr came up with his own equation that related these N's with the differences in energy between any two energy states or energy levels. So for example, if we go back and look at n equal 2 and n equal 5, just like the Rydberg equation, B is the bigger of the two. That gives us a delta E of 4.58 times 10 to the negative 19 joules. So energy states, energy levels 2 and 5 are that many joules apart from each other. Now, energy and frequency are related by this equation called Planck's equation. And if you plug that amount of energy into Planck's equation, you get 6.91 times 10 to the 14 hertz. And frequency and wavelength are related by this equation. C is the speed of light. So plugging that frequency into this equation gives us a wavelength of 4.34 times 10 to the negative 7 meters, or 434 nanometers, which is the same line in hydrogen's emission spectrum that Rydberg come up with at those same ends. So the way Bohr's theory basically explains things is that you have these electrons that are orbiting the nucleus at these different distances, technically energy states, but again, think about it either way you like. And if these electrons absorb energy, say when you put that element in a flame or run a current through it, then that will cause those electrons to jump to a higher or an excited energy state. Now, eventually they'll return back to their original state or ground state, and when they do, they'll release that energy that they absorbed earlier. And if that energy is being released at a wavelength that's part of the visible part of the spectrum, then we will see that as a colored light. So again, Rydberg's theory is based entirely on data. It saw these lines in hydrogen's emission spectrum, and it came up with a neat little equation that related those wavelengths to these ends. In Rydberg's theory, those ends were just numbers. But Bohr's equation is based on theory, and in Bohr's theory, those ends stood for the different energy levels that an electron could be at. And Bohr's theory was really important in our understanding of what was going on in an atom, specifically what was going on with the electrons as they were orbiting that nucleus. But there was one small little problem with Bohr's theory in that it only worked with hydrogen's emission spectrum. If you tried it with any other element, he couldn't match all the lines in their emission spectrum. Now, that doesn't mean his equation was a total bust. I mean, it was a big enough deal that he won the Nobel Prize in chemistry. But the fact that it only worked with hydrogen meant that there was still more work to be done. And over the next 3 or 4 decades, people eventually figured out some of the gaps that were in Bohr's theory and were able to fill in those gaps. And we were able to finally figure out what was going on with other elements in emission spectrum. But we will talk about that in another time. Bye. I'm playing Warzone.